The radio telescope dish sits silent in the darkness of rural West Virginia. Its massive curved face pointed toward a patch of sky that looks, to the human eye, completely unremarkable. Inside the control room, a graduate student named Calvin Leung watches numbers stream across his monitor, columns of data flowing like a digital river. It's just past midnight on a February evening in 2024, and he's running code he spent months perfecting. Code designed to do something that should be routine but isn't. He's trying to figure out where a signal came from. Not just approximately, not just the general direction, but exactly where, pinpointed to within a hair's width at arm's length across the vastness of space. The data resolves. The coordinates appear. Leung stares at the screen, his coffee forgotten, going cold in his hand. The source of the signal isn't where it should be. It's coming from the edge of a galaxy so old, so dead, that it hasn't formed a new star in billions of years. It's coming from what astronomers call a cosmic graveyard. And the signal itself? It carried more energy in a few milliseconds than our sun produces in an entire day. This is a fast radio burst, and nobody knows what they are. The story begins, as so many mysteries do, with someone looking in the wrong place at the wrong time and finding something they weren't searching for. The year was 2007. Duncan Lorimer, an astrophysicist at West Virginia University, had assigned his graduate student, David Narkovich, what seemed like grunt work. Sift through old data from the Parkes radio telescope in Australia, archival observations of pulsars, those rapidly spinning neutron stars that sweep beams of radio waves across space like cosmic lighthouses. Narkovich was looking at data that was already years old, observations from 2001 that had been sitting untouched in a digital archive. He was searching for patterns, for the regular clockwork pulses that mark a pulsar's signature. Instead, he found chaos. For exactly 5 milliseconds on August 24, 2001, something in the constellation Sagittarius had unleashed a burst of radio energy so powerful, so intense, that it blazed across the telescope's receivers like a camera flash going off in a dark room. The signal was there, and then it was gone. Vanished. As if someone had flipped a switch. Lorimer examined the data himself, ran it through every filter and analysis tool he had. The signal was real. It came from space, not from Earth. The radio waves had traveled through the cosmos, and as they did, they had been scattered and delayed by all the electrons and gas between their source and our planet. From that scattering, Lorimer could calculate a distance, roughly 3 billion light-years away. This wasn't a pulsar. This wasn't anything anyone had seen before. When Lorimer published his findings, the astronomical community was skeptical. Surely this was interference from a satellite or a microwave oven in the facility kitchen, or some Earth-based noise masquerading as a cosmic signal. But Lorimer had done his homework. The signal bore all the hallmarks of having traveled across intergalactic space. And if it was real, if something out there could produce this much energy in such a brief instant, then the universe was stranger than anyone imagined. They called it the Lorimer burst, and for years it remained alone. A single, unexplained flash from the dark. But then, in 2012, something happened that changed everything. Another burst appeared, and then another, and another. These weren't just random one-off events. They were everywhere, happening all across the sky, at random times, from random directions. Astronomers realized they were dealing with a phenomenon, not an anomaly. By 2020, specialized radio telescopes like the Canadian Hydrogen Intensity Mapping Experiment, CHIME for short, were detecting them by the hundreds. In 2021, astronomers reported finding over 500 in a single year. These fast radio bursts, or FRBs, were exploding across the cosmos at a rate of several thousand per day. Think about that. Right now, as you hear these words, somewhere in the universe, a fast radio burst is detonating with the energy of millions of suns, its light racing outward at 300 million meters per second, crossing galaxies, traversing the vast emptiness between stars. Some of these bursts happened when dinosaurs walked the Earth. Some happened before our planet even existed. And their light is only reaching us now, in this moment. A message from the deep past arriving like a bottle washed up on a cosmic shore. What's causing them? That's the question that keeps astronomers awake at night. The bursts are impossibly bright, brighter than entire galaxies, but they last only milliseconds. They release as much energy in less than a blink as our sun produces in an entire day, sometimes more. The wavelengths tell us they're coming from beyond our galaxy, sometimes from billions of light years away. And here's what makes them truly strange. Most of them happen once, never to repeat again. A single flash, and then eternal silence. But not all of them. In 2016, astronomers discovered FRB 112, a source that repeated. Again and again, flashes came from the same point in space, separated by minutes or hours or days, with no discernible pattern. This was a game changer. If the source was repeating, astronomers could watch it, study it, point every telescope they had at that patch of sky, and wait. They traced FRB 112 to a dwarf galaxy 3 billion light-years away. This galaxy was small, strange, dominated by regions of intense star formation and wrapped in a powerful magnetic field. It was an environment of chaos, of violence, of stars being born and dying in rapid succession. And somewhere in that maelstrom, something was producing these bursts. But what? One theory emerged above the others. Magnetars. Imagine a neutron star, already one of the most extreme objects in the universe. Take a star with more mass than our sun and compress it down to the size of a city. The gravity becomes so intense that a single teaspoon of its material would weigh as much as a mountain. The magnetic field becomes so powerful that, if a magnetar were located halfway between Earth and the Moon, it would erase the magnetic strip on every credit card on the planet. If you got within a few hundred miles of it, the magnetic field would be strong enough to disrupt the electromagnetic bonds holding your atoms together. You would cease to exist, not through any dramatic explosion, but through simple disintegration at the molecular level. These are magnetars. And in 2020, astronomers caught one in the act. Inside our own Milky Way galaxy, just 30,000 light-years from Earth, a magnetar designated SGR 1935-2154 unleashed a blast of radio energy that fit every characteristic of a fast radio burst. It was thousands of times weaker than the bursts detected from other galaxies, but it was also thousands of times closer. At its true distance, had it been as far away as most FRBs, it would have been indistinguishable from them. For the first time, astronomers had direct evidence of what could cause these enigmatic flashes. The magnetar's surface had cracked, a starquake, and the sudden reconfiguration of its magnetic field had launched a burst of electromagnetic radiation into space, like a shockwave. Problem solved, then. Fast radio bursts come from magnetars. Except the universe, as always, refuses to make things simple. In January 2025, Calvin Leung and his team at the Chime Observatory published their findings on FRB 2024-0209A. Using a new technique that involved combining data from multiple telescopes spread across North America, they pinpointed the burst's origin with unprecedented precision. The location stunned them. The burst had come from the outskirts of an elliptical galaxy, a massive structure filled with ancient, red stars that had long since exhausted their fuel. This galaxy was a graveyard. No new stars were forming here. No massive stars were exploding in supernovae. No magnetars were being born. Elliptical galaxies are where stars go to retire and slowly fade away over billions of years. They are quiet, stable, boring. And yet, from the edge of this cosmic cemetery came one of the most energetic events in the universe. The burst originated not from the galaxy's center, where you might expect unusual activity, but from its distant outskirts, over 130,000 light-years from the galactic core. Even more bizarre, another fast radio burst detected earlier, FRB 2022-06A, was traced by the Hubble Space Telescope to a cluster of galaxies in the process of merging. A violent cosmic collision occurring when the universe was only 5 billion years old. The source environment was completely different from FRB 121102, completely different from anything predicted by the magnetar theory. It was as if every time astronomers thought they understood these bursts, the universe presented them with a new impossibility. Some fast radio bursts repeat, others don't. Some come from young, star-forming galaxies. Others come from ancient, dead ones. Some pulse on a regular 16-day cycle. Others are completely random. In 2025, MIT researchers studying FRB 2022-1022A found something that narrowed down the mystery slightly while simultaneously making it stranger. By analyzing the way the burst's light twinkled as it passed through space, an effect called scintillation, they determined that the burst had originated incredibly close to its source, within 10,000 kilometers of a rotating neutron star. That's less than the distance between New York and Singapore. At such close range, the burst had to have erupted from the neutron star's magnetosphere, that region of space immediately surrounding the star where magnetic fields are so extreme, they're at the very limit of what physics allows. This was the first conclusive evidence that at least some fast radio bursts originate right at the surface of these extreme objects. But it still didn't explain the diversity. It didn't explain why some bursts came from old galaxies. It didn't explain why some repeat and others don't. It didn't explain the periodic ones, like FRB 180916b, which flashes during a 4-day window every 16 days and then goes silent, as if something is covering and uncovering the source on a regular schedule. Some astronomers have suggested that the bursting object might be orbiting a black hole surrounded by a disk of material that periodically blocks the signal. Others propose a magnetar spinning on its axis, its bursts only visible when the beam points toward Earth like a lighthouse. But these are educated guesses, shots in the dark. The truth is, after nearly 2 decades and thousands of detections, fast radio bursts remain one of the deepest mysteries in modern astronomy. And they're not the only mystery that has astronomers questioning everything they thought they knew. On October 19, 2017, a different kind of discovery sent shockwaves through the scientific community. Robert Warwick, an astronomer using the Pan-STARRS 1 telescope on the island of Maui, noticed something unusual moving across his field of view. At first he thought it was a comet or an asteroid, just another chunk of rock drifting through our solar system. But as more observations came in, as other telescopes turned to track the object, the numbers told a different story. This object was moving too fast. Far too fast. It was traveling at nearly 200,000 miles per hour relative to the Sun, a speed that could only mean one thing. It wasn't bound to our solar system. It had come from somewhere else, from another star. The object was given a name, Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It was the first confirmed interstellar visitor ever detected passing through our solar system. And from the moment astronomers began studying it, nothing about Oumuamua made sense. The light it reflected changed in a strange way. As it tumbled through space, spinning end over end every 7 hours, its brightness fluctuated wildly, dimming and brightening by a factor of 10. This told astronomers that the object was highly elongated, shaped like a cigar or a needle, roughly 400 meters long but only 40 meters wide. Nothing in our solar system has that kind of shape. No asteroid, no comet. The closest comparison was a ratio of 3-to-1. But Oumuamua was 10-to-1, an impossible geometry that defied explanation. And then there was the question of what it was made of. When comets approach the Sun, they warm up. The ice on their surface sublimates into gas, creating the characteristic bright coma and tail that trail behind them. But Oumuamua had no coma, no tail, no visible outgassing at all. It looked like an asteroid, a dead, rocky object. Yet as astronomers tracked its trajectory, they noticed something impossible. It was accelerating. Not much, just a tiny, almost imperceptible push, but enough to be measured. It was moving away from the Sun faster than gravity alone could explain. Something was pushing it. But what? When comets outgas, the jets of material act like tiny thrusters, giving the comet a small kick that alters its trajectory. This is well documented, well understood. But Oumuamua had no visible jets, no dust, no gas, nothing that could account for the acceleration. The scientific community erupted into debate. Some astronomers proposed that Oumuamua was made of nitrogen ice, a remnant of a Pluto-like world from another star system, and that its extreme shape was the result of evaporation. Others suggested it was made of hydrogen ice, formed in the cold depths of interstellar space, and that the Sun's heat was causing this hydrogen to sublimate invisibly, providing the acceleration without a visible coma. One Harvard astronomer, Avi Loeb, suggested something far more controversial, that Oumuamua might be an artificial object, a light sail or probe built by an extraterrestrial civilization. The idea exploded across the media, capturing the public imagination. Could this be our first contact with alien technology? Had another civilization sent something across the stars, and by sheer chance, did it happen to pass through our solar system just as we had developed the technology to see it? Most astronomers dismissed the idea. The evidence simply didn't support it. But they couldn't dismiss the mystery. In 2023, a team of researchers led by Jennifer Bergner at the University of California, Berkeley, proposed what may be the simplest explanation yet. They suggested that Oumuamua started its life as an ordinary, water-rich comet orbiting a distant star. Over millions of years, as it drifted through interstellar space, cosmic rays, high-energy particles emitted by supernovae, and other violent events bombarded the comet, penetrating its icy surface. These cosmic rays had enough energy to split water molecules, breaking them apart and forming molecular hydrogen, which became trapped inside the ice. When Oumuamua passed close to our Sun, the heat didn't cause the ice to evaporate, not immediately. But it did cause the ice's crystal structure to shift, creating cracks and channels. The trapped hydrogen escaped through these pathways, providing the mysterious acceleration. Because hydrogen is so light, it wouldn't have dragged much dust along with it, explaining why there was no visible tail. The theory is elegant. It fits the observations. It explains the acceleration, the lack of a coma, even the strange elongated shape, which could be the result of the object slowly eroding as it tumbled through space for millions of years, like a bar of soap wearing down in the shower. But here's the maddening part. We'll never know for sure. Oumuamua is gone, already past Neptune's orbit and heading back into the depths of interstellar space. No telescope on Earth can observe it anymore. It's too far, too faint, too small. Whatever secrets it holds are leaving with it, disappearing into the cosmic dark. And we are left with questions. How many other interstellar visitors pass through our solar system without us noticing? Astronomers estimate that within the orbit of Neptune, right now, there could be 10,000 Oumuamua-sized objects, each one a wanderer from another star. Most of them are too small, too dim, too fast for our current instruments to detect. They drift through the space between planets like ghosts, invisible travelers on journeys that began before our species existed. In 2019, astronomers detected a second interstellar object, Comet 2I Borisov, which behaved exactly like a normal comet, complete with a bright coma and tail. And in 2025, a third interstellar visitor, designated 3I Atlas, was identified. But Oumuamua remains unique, an outlier, a puzzle that refuses to fit into any neat category. And somewhere out there, drifting through the dark between stars, are billions more objects like it, each one a messenger from alien worlds, carrying stories we may never hear. But if Oumuamua challenges our understanding of what objects in space can be, there is another mystery that challenges our understanding of stars themselves. 1,470 light-years from Earth, in the constellation Cygnus, there is a star that should not exist. Not because it's unusual in its composition or its size. By all accounts, it's a fairly ordinary F-type main sequence star, slightly larger and hotter than our Sun. No, this star is impossible because of what it does, or rather, what something near it does. The star is designated KIC 84628552, but astronomers call it Tabby's star, named after Tabitha Boyajian, the astronomer who first brought its bizarre behavior to the world's attention. And that behavior is this: the star dims, randomly, unpredictably, sometimes by just 1%, sometimes by as much as 22%. And these dimming events can last for hours, or days, or weeks, with no pattern, no regularity, no explanation. The discovery came from an unlikely source. Between 2009 and 2013, NASA's Kepler Space Telescope stared at a patch of sky in Cygnus, monitoring the brightness of over 150,000 stars. Kepler was designed to find planets by detecting tiny, regular dips in starlight as planets passed in front of their host stars, blocking a fraction of the light. A Jupiter-sized planet might block about 1% of a star's light. An Earth-sized planet might block 1/100%. These transits are predictable, periodic, clockwork events. But KIC 84628552 was doing something else entirely. The dimming was erratic. It had no period. The depth varied wildly, and the dips were massive, far too large to be caused by a planet. In 2011, the star dimmed by 15% over several days. In 2013, it dimmed by 22%. Whatever was blocking the light had to be enormous. half the diameter of the star itself. And it was in orbit, or at least moving in front of the star, but not in any regular pattern. The data was so strange that at first, astronomers thought it must be an error, a glitch in the Kepler telescope's instruments. But the signal was real. And when citizen scientists participating in the Planet Hunters project, a crowdsourced effort to analyze Kepler data, flagged the star as bizarre and interesting, professional astronomers took notice. Tabitha Boyajian, then at Yale University, led a team to investigate. They examined every possible natural explanation. Could it be a swarm of comets? Comets are dirty snowballs that release gas and dust as they orbit close to a star, and a large group of them could, in theory, block significant amounts of light. But comets follow predictable orbits. They come and go on regular schedules. Tabby's star's dimming had no schedule. Could it be a debris disk? The shattered remnants of a collision between large asteroids or planets? But debris disks are usually smooth, symmetric structures. They don't cause irregular, dramatic dips in brightness. Could it be something passing between us and the star? Something in our own solar system? But the color of the dimming ruled that out. When objects within our solar system pass in front of distant stars, they block all wavelengths of light equally. Tabby's star's dimming was wavelength dependent. More blue and ultraviolet light was blocked than red and infrared light. This meant whatever was causing the dimming had to be far from Earth, close to the star itself, and small enough that it interacted with light rather than simply blocking it. Dust. The culprit had to be dust. But that just raised more questions. In 2016 and 2017, Boyajian launched a crowdfunding campaign that raised over $100,000, the money funding on continuous observations of Tabby's star using the Las Cumbres Observatory Global Telescope Network, a collection of robotic telescopes scattered around the world. The idea was simple. Catch the star dimming in real time and study the event across multiple wavelengths of light. If the dimming was caused by solid opaque objects, like planets or megastructures, the dip in brightness would be the same at all wavelengths. If it was caused by dust, different wavelengths would be affected differently. In May 2017, the star began dimming again. Telescopes around the world swung into action, observations poured in, and the results were clear. The dimming was wavelength dependent. Dust was the answer. But not the end of the mystery, because the dust itself is strange. It's incredibly fine, much finer than cigarette smoke, composed of particles smaller than a micrometer. Dust this fine should be blown away by the star's light pressure, pushed outward into interstellar space. Yet it remains, orbiting the star. This means there must be a constant source replenishing it, something generating new dust as fast as the old dust is blown away. And there's another problem. The dust is cold. If it were close to the star, it would glow with infrared radiation, heated by the starlight. But observations from the Spitzer Space Telescope show no significant infrared excess. The dust must be far from the star, out in the cold outer reaches of the system. So something out there, far from the star, is continuously producing vast quantities of extremely fine dust, enough to block up to 22% of the star's light. What could do that? A massive collision between planets? A disintegrating moon? A swarm of comets undergoing continuous fragmentation? Or something else? Something no one has thought of yet. In 2019, astronomer Edward Schmidt analyzed data from the All-Sky Automated Survey for Supernovae and identified 21 other stars that exhibit similar dimming behavior. 15 of them are slow dippers, dimming gradually and irregularly, much like Tabby's star. 6 of them are extreme dippers, showing even more dramatic fluctuations. This means Tabby's star is not unique. Whatever is causing this behavior, it's happening elsewhere, to other stars, in other systems. It's a phenomenon, not a fluke. And we still don't fully understand it. There was, of course, the alien megastructure hypothesis. In 2015, astronomer Jason Wright at Penn State University raised the possibility, however remote, that the dimming could be caused by artificial structures built by an advanced extraterrestrial civilization. Imagine a Dyson swarm, a collection of solar panels or habitats orbiting a star, harvesting its energy. If such a structure were incomplete or undergoing construction, it might block starlight in irregular patterns as new components were added or moved into place. It was a tantalizing idea. It captured the public imagination, but the evidence doesn't support. An opaque structure, whether natural or artificial, would block all wavelengths of light equally. Tabby's star's wavelength-dependent dimming rules out solid objects. The megastructure hypothesis is, by all scientific measures, dead. But it served a purpose. It got people interested. It got funding for observations. It reminded us that sometimes the most boring explanation is still incredibly strange. And here's the truly haunting part. Tabby's star has been dimming over the long term. Archival photographs going back to 1890 show that the star has faded by roughly 20% over the last century. This isn't the short-term, erratic dimming. This is a slow, steady decline in brightness, as if something is gradually enveloping the star, blocking more and more of its light year after year. What could cause this? No one knows. Dust clouds don't last for centuries. Comets don't stay in front of a star for 100 years. Planetary collisions are one-time events, not ongoing processes. The star is changing, and we're watching it happen in real time, and we have no idea why. These are the kinds of mysteries that keep astronomers up at night. Not because they're unsolvable, but because every answer leads to new questions. Every explanation reveals new depths of strangeness. Fast radio bursts that come from cosmic graveyards where nothing should be happening. Interstellar visitors with impossible shapes that accelerate without visible means. Stars that dim and brighten as if something vast and inexplicable is moving in front of them. These are not ancient mysteries, relics of a time before we had the tools to understand the universe. These are modern mysteries, discovered with our most advanced telescopes, our most sophisticated instruments. They are happening now, unfolding in real time, and they are forcing scientists to question fundamental assumptions about how the cosmos works. What produces bursts of energy so bright they outshine entire galaxies? What kinds of objects can survive the journey between stars? And what do they tell us about the worlds they came from? What processes can surround a star with enough fine dust to block a fifth of its light? We like to think we understand the universe. We've mapped the cosmic microwave background, the afterglow of the Big Bang. We've detected gravitational waves, ripples in space-time itself. We've imaged black holes, those regions of such extreme gravity that not even light can escape. But for all our knowledge, for all our telescopes and satellites and supercomputers, the universe still holds secrets. It still surprises us. It still shows us things we never expected, things we didn't even know to look for. And here's what makes these mysteries so compelling. They're not theoretical. They're not thought experiments or mathematical abstractions. They're real. They're out there, happening right now. Somewhere in the universe, a fast radio burst is erupting, its light beginning a journey across billions of light years. Somewhere, an interstellar object is drifting past a distant star, tumbling through the dark, a wanderer with no home. Somewhere, a star is dimming, and no one knows why. These phenomena are clues, breadcrumbs left by a universe that is far stranger and more complex than we ever imagined. They remind us that we are still explorers, still peering into the dark with imperfect instruments and incomplete understanding. They remind us that the cosmos is not a solved puzzle, but an ongoing mystery, one that invites us to keep searching, keep questioning, keep looking up. Because the universe, it turns out, has a sense of drama. Just when we think we've figured something out, just when we're ready to close the book on a mystery, it throws something new at us. A burst from a dead galaxy, an object with an impossible shape, a star that flickers like a candle in the wind. And every time, we're left standing in the dark, staring up at the sky, asking the same question humans have asked for millennia. What else is out there? What else don't we know? What else lies hidden beyond the edge of our sight, waiting to be discovered? The truth is, we're still at the beginning. We've barely scratched the surface. The universe is vast, ancient, filled with wonders and horrors and mysteries that will take generations to unravel. And somewhere out there, in the deep black between stars, in the hearts of distant galaxies, in the ruins of solar systems long since dead, the universe is waiting. Waiting for us to find the next impossible thing. Waiting to show us something new. Waiting to remind us once again that no matter how much we learn, there will always be more questions than answers. And maybe that's exactly as it should be. Maybe the mystery is the point. Maybe the search itself is what makes us human. Because as long as there are stars that dim for no reason, as long as there are signals from nowhere, as long as there are visitors from other worlds tumbling through our cosmic neighborhood, we will keep looking. We will keep searching. We will keep asking why. And the universe, in its vast and incomprehensible way, will keep answering. Not with solutions, but with more mysteries. Not with certainty, but with wonder. And that wonder, that sense of standing at the edge of the unknown and peering into the dark, is perhaps the greatest gift the cosmos can give us, because it means there's still more to discover. It means the story isn't over. It means that out there, somewhere, in the infinite expanse of space and time, something is waiting. Something strange. Something impossible. Something that will make us question everything we thought we knew. And all we have to do is keep watching the sky.